All right. First, what I'm going to do is people have asked for the solutions, so before every lecture I'll post one of the solutions. So this is the solution for the circuit problem from test 1. You can just take a look at it, and on the lecture you can just freeze frame it and then just stare at it as much as you'd like. What we're going to do is, yesterday we talked about electromagnetic induction. Yesterday we talked about Faraday's law. And what we're going to do is we're going to go over some permutations of, there are two main types of problems, that one and this one. Here there is a static area changing B. And over on the right we have a changing A and a static B. So in one case the area is changing, in the other case the B field is changing. Both of these follow Faraday's law in the sense that the electromotive force produced is negative d phi b dt. And the negative sign is because of Lenz's law. So what I typically do is I use, the way that I think of electromotive force is I think of the magnitude, the absolute value, and that is equal to d phi b dt, and use logic to determine signs and direction. So in this type of problem, so we're going to use logic to determine the sign and the direction of all this stuff. And with this, so in problem 1, because it's the B that's changing the electromotive force, and from now on I'm just using, think of these always as magnitudes, is that it is area dB dt, because magnetic flux is B times A. For 2, the electromotive force is B dA dt. And because A is Lx, dA dt ends up becoming LV. So this is simply BLV. And what I want you guys to do is on the test, one of these will be on the test, and depending on, and for sure the other one will be on the final. Depending on how well you do on the test problem, if you guys do great on it, you won't see it on the final except for the other one. If you don't do great on it, then you may end up seeing it as like an appetizer or something. The easiest one to think about is the circle. So with the circle, what I'm going to do is here the initial B field is out. Here the initial B field is in. Now what I'm going to do is there are several different arrangements for something like this, and that is that dB dt is out, or dB dt is in. In a case like this is the one that makes the most sense. It goes 2 Tesla out of the page, 3 Tesla out of the page, 4 Tesla out of the page, and so on. For something like this, it starts off at 2 Tesla out of the page, 1 Tesla out of the page, no magnetic field, etc. So seeing your confusion right now, because you just made that scrunchy face, let me plot it out. If I was to plot out B as a function of time, it would look like that. That the B field would be steadily increasing. And something like, so really the dB dt is just the slope of the B field. For something like this, it would look like that. That eventually it would reach 0 and then end up at a negative value. For these two, we'd have dB dt out, or dB dt in. So this is a lot like that in the sense that it starts negative and it continues to be negative. For this one, it starts negative and then becomes positive. Actually, I need to walk. Hold on. What am I going to do? I'm going to unlock the door. So those are the 4 arrangements that we could have for the circle. It's either going to start positive and become more positive, or start positive and eventually become negative, and then it has its counterparts for when the B field is initially in the other direction. So Faraday's law does not care about the B field. It does not care about area. It only cares about the change in magnetic flux with respect to time. So in all of this case, a lot of times people go, well, but the B field is out or the B field is in, and that is irrelevant. What is relevant is, what does the change in flux look like? Now in the situations above, the magnetic flux, and I'm going to draw the initial magnetic flux, is always in the same direction as the B field. So that flux on the top two are out initially, the flux on the bottom two are in initially. these two would eventually flip their signs because the dB dt is in the opposite direction. Now, the d phi b dt, actually I'm going to draw it outside of the The d phi b dt is the change in magnetic flux, the change in the B times A. Well, what's doing the change? The change is the B field itself. So the d phi b dt is associated with the dB dt. So this always parallel to d phi b dt. So in all of these cases, I ignore what that is. All I care about is what that is. So I have this. So in the cases where you've got magnetic field out, the flux is out. In cases where the magnetic field is in, the flux is in. But the flux coming in or out doesn't really matter. It's the change in flux. What is changing about these problems? The magnetic field. So in cases where the magnetic field is changing outward, the change in flux is changing outward. In cases where the B field is going inward, then the change in magnetic flux with respect to time is inward as well. Now, according to Lenz's law, the d phi b dt induced is anti-parallel to d phi b dt. That's Lenz's law. This is where that's the crux of the of magnetic induction. In these circles, ideally, and eventually, if we had time, we talk about inductors and stuff. Basically, just big coils. The coil likes it the way it is. The coil likes the flux not changing. And if you change the flux on it, in a weird way, it's kind of like Newton's third law. You push on it, it pushes back. Now, there's a lot more. I mean, I've sat down and really thought about, what's going on within the material itself. But in the end, the material likes the flux being the way that it is, and if you change it, it tries to keep it at the same level. So if the change in magnetic flux is out, the induced flux is in. Oops, and I'm messing this up. So the induced magnetic flux, the induced change in magnetic flux is always opposite of this. So you could say that the induced magnetic flux is into the page here. You could say that the d phi b dt is into the page. And you can also say that the B field generated by the induction is also into the page. So those three things are all in here, all out there. So anything marked in this green stuff is the induced magnetic flux, the induced change in magnetic flux with respect to time, and the induced B field. In the last part, you have to ask yourself, well, what current produces a magnetic field that is in over here and out over there. Well, for something like that goes in, we use our little wrap rule. If the current at this point is going from right to left, my fingers claw into the page in there and out of the page here. So the current here is clockwise. So anything with the induced magnetic flux going into the page produces a clockwise current. Anything producing a B field coming out of the page, the B field goes counterclockwise. And so we get this. And so these are the 4 types. It can only be one of these 4 if I choose to give you the circle. Yes?
Will you explain like how to do the direction again?
Okay.
With the wrap roll?
Good. All right, so let me back this up. And in fact, what I'm going to do is I'm going to use a big piece of paper. I'll put this back up in a little bit. So we have a wire. The current direction doesn't really matter. It's the procedure that we're trying to learn. So let's say the current goes from left or right to left. To determine the B field, stick your thumb in the direction of the current. The fingers wrap in the direction of the B field. So on, I did this earlier, or yesterday. So let's say that this is the wire, and we're going from your right to left. So the wire has current and it's going from there to there. So what you do is you take your right hand, you put your thumb in the direction of the current. Now watch how the fingers go. When they're coming around the bottom, the fingers are pointed at you. When they go around, the fingers go in. So you watch how the fingers go. So on the bottom, they're coming at you. At the top, they're going in. Now, if we looked at it from, it's a 3-dimensional thing, so this is where it's where it gets weird. If the current is headed right at you, put your thumb in the direction, so how does the B field look like? It looks like a circle. The B field is going around like that. So down here, at the bottom, B field is going that way. Over here, it's going up. On the top, it's going that way. And on the other side, it's going down. So you have to use your right hand and then wrap those fingers. If the current is going in the other direction, change the direction of your thumb. So the fingers go out now, they now come out on the top and in on the bottom. So all it really means, and this is technically it's not the right hand rule, so obviously it isn't, But the rack rule gets the, I call it the rack rule, it gets the job done. Thumb in the direction of the current, and then the B field racks. And then if you look at it head on, current is heading at you, so the B field is in a circular fashion. Current is going away from you, now the thumb points at me, the B field rotates in a different direction. And so that's how you get it. Yes?
So for that one, you put your thumb, put your hand like this,
Yeah.
and you just wrap it down.
Yeah, notice how on the top, if I have direct, let's say I was tall enough, if I was like LeBron James tall, put my hand up there, my fingers claw into the page above the line, but below the line they claw out.
So like it would be the X on.
X on the top, circle dot on the bottom. Yeah, let me do that.
Are the B field lines coming out of the wire at a certain point, or?
B field lines coming out of the wire at a certain point. Is that what you,
Yeah,
What?
just because we were doing the first magnetic field
Mhm.
experiment yesterday, and we were working with the tangent galvanometer, and it was kind of confusing, because I was like trying to think of it as a bar magnet, where you have the magnetic fields coming out of the North Pole, and then coming back into the South Pole.
in a way, it's like, they're similar, but it's no, it's not, I'm sitting here trying to think of it in English, what it is. It's almost like this is within the magnet, or just outside the magnet, where the North Pole is over here, or the South Pole is over there, and oh, actually, hold on, I'm thinking about it. No, it's nothing like that. And just speaking briefly about how nifty the B field is, it's like you've got the Earth. That's a sweet Earth, and it's what happens is you've got the north end and the south end geographically, but what is the Earth? At the core of the Earth, most of the Earth is dead and sterile. Most of the Earth is just this big molten ball of iron that's rotating. And that rotating iron produces a magnet effectively, where the magnetic south and the magnetic north is like that. So the magnetic north is the geographic south and vice versa. And the fun thing about that, people talk about, oh, the static nature of the universe. That magnetic field for the Earth is bouncing around. The magnetic North Pole changes on the order of 10, 20, 30 kilometers a year. For a while it was in northern Sweden or Norway. Now it's over in Russia. And occasionally, and this is the freaky part, the poles flip. About every 600,000 years or so, the poles flip, which causes an interesting effect on migratory animals, things that use the magnetic field. It's fascinating. So really, when you look at this is a wire, and what I'm going to do is, think of this circle, but only think of that wire right there. What is it doing? It looks a lot like this, but blown up. The inside of the wire is to the left, the outside of the wire is to the right. The current goes up, which means the B field on the inside goes up, the B field on the outside goes in. For something like this, the current is on the bottom to the left. We could put the paper like this. This is parallel to that segment. The B field above the wire is in, the B field below the wire is out, much like we've set up here. This little section right here is blown up to be all of that. So these are the 4 things, and one of the things I'm going to do right now is do the typical example that I do with problems like this. So we have an initial magnetic field of 2 Tesla out. And the real question is, will the B field reach 5 Tesla out or 5 Tesla in first, and when? So that's the question. Let me set it up. So we've got this external B field. It's 2 Tesla coming out of the page. I want to know, is this B field going to go to 5 Tesla out or 5 Tesla in? And how long is it going to take? Well, the resistance of this loop is 5 ohms. The area, I'm not going to play games with circles and stuff like that. I'm just going to give you the area, is 3 square meters. And the current flowing through the system is 0.25 amps counterclockwise. So the current is running in a counterclockwise fashion. Well, if the current is running in a counterclockwise fashion, we only have 2 choices for this. If the current is running like this, the induced magnetic field and flux has to be out. If the induced flux has to be out, the external change in flux has to be in. If the external change in magnetic flux has to be in, the external change in B field with respect to time must be in as well. So this change in B field is going into the page, which means it is not going to go 2 Tesla, 3 Tesla, 4 Tesla. It's going to go 2 Tesla, 1 Tesla, 0 Tesla, -1 Tesla, down to -5 Tesla. So it looks, the plot will look a lot like this. So if this is -5 and this is 2, I got to figure out that time right there. Well, let's set up some equations. Current is the electromotive force divided by resistance. The electromotive force is area dB dt divided by resistance. Because electromotive force is d phi b dt and phi b is BA. So solving stuff for dB dt, IR over A is equal to dB dt. Now these are all magnitudes. I'm only interested in the magnitudes of these things. What I found is that if you've got tons of negative signs flying around, the student tends to get overwhelmed. So I keep magnitudes and I use logic for everything else. So the change in B field with respect to time is I 0.255 over 3. So 1.25 over 3. And I get 0.417 Tesla per second. Now this is 0.41 Tesla per second going into the page. So what we're going to do is we're going to take our velocity equation and shift it a little bit. The V equals V naught plus AT will become B equals B naught plus dB dt times time. So in a way that we're treating the acceleration like the change in magnetic flux. The initial velocity is the initial B field and then the final. So because I know that the change in magnetic field is going into the page, it's got to hit -5 before, and it's impossible to hit 5. So final B is -5, B naught is 2, dB dt is -0.417. So let's get this straightened out. B minus B naught equals dB dt times time. So B minus B naught over dB dt is equal to time. My initial B is 5. Or I'm sorry, my final B is -5. My initial B is 5. My dB dt is -0.417. So -10 divided by and I get so close that I'm willing to round it off, 24.0 seconds.
Professor Schubert,
Yes.
I'm just trying to see over here kind of how you put that together after you have the A.
This?
Yes.
Okay. What I did, now let me get it blown up so that we can really take a look at it. So I have a loop, and in these types of problems, there are all sorts of, I can ask for all sorts of variables, but in this variable, I gave you the current, 1/4 amp, and I also told you that the current was counterclockwise, that's a given. So if this current is the induced current. So if the induced current is counterclockwise, the current at the bottom is to the right, which means my fingers crawl out of the page above it, which means that the induced magnetic flux, the induced B field, all have to be out of the page. It has to. In order to get that induced flux to come out of the page, the external change in magnetic flux has to be in, according to Lenz's law. In order for the external change in flux to be into the page, the B field must be into the page as well. Because if the change in B field was coming out, the external change in magnetic flux would have to be out as well. So this lets me know that I'm not going to go from 2 to 3 to 4, because that would mean that this had to have been a circle dot. Instead, it's a circle cross, which means it's going to go from 2 to 1 to 0 to -1 and so on, which means that it is not going to go to 5, which is 5 out. It's going to go to -5, which is 5 in. And that's how I reason it out.
Why did you use 5?
Because I chose so. I just-
in the problem.
Why did I choose 5 Tesla in the problem? Is that the question?
Like if BO is 2, like the initial.
The B initial was 2 because I said so. I had to pick some numbers, 1 on either side. So I just picked 5, and for symmetry, I said 5 in.
So you meant to use 2.
It was intentional. And so you could do this with all sorts of things. This equation, know how to set that up, and you could be able to solve for all the variables. Know how that equation is set up and be able to solve for all variables. And if you can handle those two things, you've got everything. Yes?
Okay, this may not be a good question, but how do you know when you use dv over dt and not like dA over dt?
In this circle, is the area changing?
Yes.
I guess not, or you know not.
I definitely don't know.
It's not changing, it's a circle. Did I ever say that the circle was getting bigger or smaller? Did I say that anything was physically moving? No. So this has to be the change in magnetic field. Now, let me reassure the class. Either it's going to be a problem where the B field changes and nothing else, or the area changes and nothing else. This is the classic problem where the area does not change. If it's a circle, the area doesn't change. If it's this guy with the moving bar, that means the area is changing. I'm not going to give it to the class, but I have a problem where the B field changes and the area changes, and it's delicious. But I would say that's for Cal-based students or honors. I would totally throw it in an honors class. I would destroy them. But it's not, so it's sweet, yeah. All right, so these are the four types in your problem sets. You can kind of look at it and go, oh, then it has to be like this, and then you just remember all the signs and everything. But there's a logic to all this nonsense. Now let's discuss the other category of problems. And what I'm going to do is, we'll do two at a time. So here, you have two long wires and a resistor, and here you have a bar. The B field is out in this case. So in both cases, the B field is out. The next sheet will do the B field is in. And here, the velocity of the bar is to the right. Here, the velocity of the bar is to the left. The area that we're thinking about is there. So let's first talk about areas of these circles. If the bar is heading to the right, that shaded region, is it getting bigger or smaller? Bigger. So the area is increasing. For the bar headed to the left, is that area increasing or decreasing? It's decreasing. So in this particular case, the magnetic flux is always parallel with the B field. Parallel to parallel, parallel to parallel. So the magnetic flux is always parallel to the B field. Now what interests me is the change in magnetic flux. Here, the area is getting bigger, which means there's more magnetic flux that's coming out of the page. So initially it's 2 Tesla meters squared, then 3 Tesla meters squared. So if I draw this, that magnetic flux is increasing, which means that the change in magnetic flux is also out. It's positive. The slope of that line is positive, so that has to be positive. In this particular case, on the bottom, the area is getting smaller, which means that the magnetic flux coming through the window decreases, which means that the magnetic flux looks more like that. Which means that the d phi b dt is into the page as well. So if the area is if the area is getting bigger, those two are parallel. If the area is getting smaller, those two are anti-parallel. Now Lenz's law kicks in. Lenz's law says, I don't give a rip about flux, I don't give a rip about the B field, all I care about is the change in flux. Change in flux there is out. So the induced change in flux is in. Here the change in flux with respect to time is in, so the induced change in flux with respect to time is out. And so that is Lenz's law being applied. The last part, well, what produces a magnetic flux or a change in magnetic flux that's going into the page, which means that my magnetic flux and B field have to go in as well. Into the page means that my induced current must be clockwise. Put your thumb in the direction of that current. It claws above the line, so a clockwise current will produce that. For this, the current goes like out, or the flux goes out like that, so the induced current is counterclockwise. For all of these cases, the electromotive force, which is d phi b dt, and I'm only interested in magnitudes at the moment, this gives you b dA dt, which gives you b L dx dt, which gives you b L v. So the current is B L V over R. And I'm only using the magnitudes. I don't care about the directions. So that's the current flowing through. Now, the thing that's different about this than this is with a circle in a B field and the current is going through the circle, the forces, I mean, it's a current in a magnetic field, so there should be forces, but they cancel because they're going in all different directions. For this, the only part that moves is the bar. So the force due to magnetic field is I cross B. And I'm only interested in the directions with this. As written, that's a direction equation, not, I mean, I'm not going to get any numbers out of it. So for the top, the B field is out, the current is top to bottom, so I cross B is out, so the magnetic force is left. Here, I is to the top of the page, B field is out, thumb points right, so the magnetic force points to the right.
Did you say that the magnetic force is always opposite of the velocity?
Yeah, what you find out is you make an observation. You make the it is true. The magnetic force will always be opposite of velocity. If I use it as a check, if it isn't opposite of velocity, I've messed up somewhere.
Is it just coincidental that where you placed your area on the diagram too, that the induced field kind of goes that direction?
What I'm doing is I'm going through all 4 permutations. In this permutation, the B field is out. I only have 2 choices now, increasing or decreasing area, and those 2. So, does that answer? I'm not sure of the...
No worries.
Okay.
I mean, I understood it the way you put it too.
Okay. I heard the word coincidental, and that makes me queasy a little bit. Okay. This force, I mean, we use the current balance. F is equal to ILB. I is BLV over R. So I L squared B squared over R is the magnitude of the force. To keep V constant, to keep B constant, you have to have an external force. This external force is generally applied by the person either pushing or pulling the bar. And it is always opposite of the magnetic force. So you could say that the external force will always be applied in the direction of velocity. Now you just can't come out and say it. What I want you to do is go through the steps and rationalize it out. And if you know the answer anyway, you can kind of like reverse engineer it and kind of think it through. But those are the 2 cases, the one where the B field is out of the page. And those are, be able to get those equations, and then you can manipulate them. The other 2 examples, well, it's the same thing, but the B field now is in, and we can move a little faster. Now the equations are all the same. And once again, one goes to the right, one goes to the left, but the B field now is in. The area is still this highlighted region. The magnetic flux is always in the direction of, well, first let's do this. Area increases, here area decreases. The magnetic flux is always parallel to that, so the B field, or actually, magnetic flux is in, magnetic flux is in as well. In this particular case, that's the magnetic flux as a function of time. It starts negative and it becomes more and more negative, or more and more into the page. For this situation, it starts negative but slowly creeps up to 0 because the area is getting smaller. There's less magnetic flux going through the window, so effectively you're ending up with a positive slope. That slope is the change in magnetic flux with respect to time. So here, the d phi b dt is into the page, the d phi b dt is out of the page. It's according to the slope. Now Lenz's law goes, wait a minute, I can't handle this. So the induced d phi b dt, or phi b, or b, is out of the page. Here, it has to be into the page. It's always opposite. This is always opposite to that. To produce a magnetic flux that's coming, an induced magnetic flux coming out of the page, well, look at this. It has to be a counterclockwise current. To get the induced magnetic flux to go in, the current has to be clockwise. So that sets the current. The last bit is the bit dealing with the magnetic force. Here, the current is going to the top of the page. The B field is in, so the magnetic force is to the left. To have the magnetic force to the left and the velocity constant, there has to be an external force to the right. To keep that so that dV dt is 0. Here, the current is going down to the page. Oh, let's see, how am I going to do this? I'll do it in front of you because I'm going to crack my wrist. On the bottom one, the current is down towards the floor. The B field is into the page, so the thumb points in that particular direction. The external force is, or I'm sorry, the B force is to the right. Which means to keep the force constant, or to keep the velocity constant, the external force is to the left. So what we see here are the 4 permutations of the moving bar. It can only be one of these 4 if I give you a moving bar problem. The observations that we make is A, that, well, the biggest one is that the magnetic force is always opposite of velocity. It's not a law, it's just an observation made through by experimentation. So you can do the logic, and if the current produces a magnetic force that is in the same direction as velocity, you know you've messed up and you need to go back and rethink it. And so that's it. For one of the, we now know 2 out of the 3 for sure. One is Kirchhoff's law, find the current in the middle resistor, up or down in magnitude. And then the next one will be either this, or it's circle like this. For something like this, what I'll typically ask is, give me the force or the current or the length or the velocity, stuff like that. And one of the real questions that I gotta ask is, what's wrong about that problem there? How do I need to fix this? There's no velocity. Should be a V. Because the I is the substitution. I gets substituted out, so. Whew. So those are everything that we need to know about that. Let me take a look at what we got. So we've completely covered problem 5. Problem set 6 does some weird things, hybrid problems. Problem 5 on problem set 6 we did yesterday effectively. Problem 6 on problem set 6 is me just being mean. Have fun with it. Think about it. Probably what'll end up happening is I'll do it in class or tack it on. I probably won't grade it, but we'll just do that. What I'm gonna do is a smattering of problems that I need to be covered. All right, what I'm gonna do now, problem set 4, page 4, E. I originally encountered this problem as an undergrad, and the TAs gave this problem to us. And they said, all right, we're gonna write this problem down. We're gonna give you about 10 seconds to freak out, and then we're gonna tell you how to do it. And then it'll be okay. It's a lot like bringing in a Bengal tiger, but the Bengal tiger is in a cage. It's not gonna hurt you. So I'm gonna show this problem to you and how it's not that bad. Here, we magically have a current appearing at the center and radiating outward, and we have 3 different arcs. And I give you the radii of those arcs. And I say that also, when it comes to this, there are physics reasons why. You can ignore the parts of the wire that are aimed directly at the center. I'm only interested in the B field contributions made from the arcs, not from those little lines. In the end, the little lines aimed at the center have no effect in a 214 world. I'm only interested in the arcs. So the total B field is the B field from arc 1 plus the B field from arc 2 plus the B field from arc 3. They just add up. Much like masses, moment of inertias, E fields, potentials, all sorts of stuff. For an arc, it's mu naught I over 4 pi r. Oh, mu naught I, and what's the missing? The what? N? Theta, correct. We only have, effectively, these arcs are only singular arcs. There's not multiple arcs. I know where the N came from, and that's from the coils that you guys used yesterday. This is so I understand that answer. If it was, let's say we looped it 50 times, so we went around, and then we went around, and we went around, a total of 50 times, then yes, there would be an N there of 50. So this becomes mu naught I theta 1 over 4 pi R1 plus mu naught I theta 2 over 4 pi R2 plus mu naught I theta 3 over 4 pi R3. Now this is the same length of wire, so the I's are all constant. They're the same. Factor it out. Mu naught I over 4 pi theta 1 over R1 plus theta 2 over R2 plus theta 3 over R3. And so we just added them up. Now we may plug and chug. 4 pi times 10 to the negative 7 I over, or I is, what did I give as I? 0.3. There's a 4 pi. So those cancel. R1 is 0.1. R2 0.2. R3 is 0.3. So now we have two things to determine. One, the values of the thetas, and two, the sines. For the first two arcs, that arc and that arc, they are semicircles. So the number of radii in semicircles is pi. You have to use radians in this. The last one is a quarter circle. So 2 pi divided by 4. Pi over 2. Now we have everything but the sines. The current loops go counterclockwise, clockwise, and counterclockwise. What we could do is we can kind of look at this and see how a current going clockwise will produce a B field that is going into the page. So the B field contribution from this wire is into the page. The other two, the currents go counterclockwise. They produce B fields that are out of the page. So the first and third wire are positive, second wire is negative. And now, well, let me rewrite this one last time. This becomes 0.3 times pi times 10 to the negative 7, 1 over 0.1 minus 1 over 0.2 plus 1 over 0.6. That 2 comes down, and I get that. And I get 6.28 times 10 to the negative 7 Tesla. these pi's were these pi's here canceled. I factor out the pi here to get that pi right there. And so that's a simple arc problem. People all go nuts about it. It's not that bad. You see a problem like this, now you know how to do it. So if it shows up on the test, thinking about the test already, because the test is on Tuesday, we have Kirchhoff's for certain. We have magnetic induction for certain. Which means I'm left with an appetizer problem and a full problem. And this could be like B field addition. Force on a wire. Ooh, another good one. Particle spectrometer. Circular motion, because that's what particles move in a B field. They do that. I mean, that's kind of the broad strokes of what this is. Force on a wire. I see springs. Problem set 6. I definitely, okay. You guys will like this. Metaphysical certainty for the appetizer. So it's only for problem 3. For the appetizer, we're gonna do the right-hand rule game. So it'll be 5 points. Free, hopefully. You're disappointed that there's the right-hand rule?
I'm not very good at it.
You're not very good at it? Okay, well, excellent. Then it's definitely going to be on the test. So the right-hand rule game will be on it. This is just to refresh everybody. For the people who, for most everyone, except for her, who took it in June, pretty much know it already and it's fresh. For everybody who took 213 last fall, last spring, dust that stuff off because it's important and critical. So that's the right-hand rule game, which means that the last problem will be like one of these, and I don't know which. Best guess, I'll probably flip for it, and it'll be one of these 3, is my guess. Yes? Oh, you just had your hand up. You're stretching. Okay. Don't look at her. She's self-conscious. The right hand, or problem 3, I will flip for it. The magnetic induction, I'll flip for it again because it'll either be that or that, one of the two. And so that's pretty much what's going on. Now, what's really interesting is that I think I've been teaching for 7 years. The first 4 years, in my opinion, test 2 of 214 was the hardest in terms of, I think it's the hardest in terms of conceptual visualization skills. But what I found out is as I get better in teaching it, and I'm pretty darn good if I must say myself, test 2 of 214 actually has gotten a lot easier because I'm much better at communicating it in what's going on. So let's see. I know what we need to do. Problem set 6, number 2. Because I did give you certain bits of information. It would be helpful if I did. So how I will do my apology is by working the problem and figuring out what we need. So on number 2, and in fact, we could sit here and we can analyze it because this is a really good magnetic field force on a wire problem. You have a wire, and currently the current is going from right to left. There's going to be some changes to this problem, so tell anybody who's not here that we will definitely give some information. The initial current is clockwise in this guy. The mass of this loop is 0.005 kilograms. The current passing through the loop, I don't know how this current is passing through the loop. Actually, I'm going to write it lowercase since I typically write it lowercase. 0.4 amps. What I want to know is what is the value of the upper current such that, now this wire here is fixed. It's just it's not moving. It can't move. It's just solid. Down here is this rectangle with current flowing through it, and I want to know how how much current do I need to pump through this thing in order to keep that thing floating. So if it's floating, I know that the sum of the forces on this object is equal to 0 because it's in translational equilibrium. Now, here are the parts that I didn't give. I didn't give this distance y1, and I didn't give this distance y2. Oh, and I didn't give that distance L. So what we're going to do is we're going to do the problem alphabet soup mode, and then we'll figure out some letters and that will make it work out right and realistically. The current up here produces and hold on, let me do this real quick. Up, oh wow, okay, so I had fixed it. The magnetic field produced by this wire, I'll have it marked in red. Put the thumb in the direction of the current, fingers crawl in the Elmo on top, they crawl out of the Elmo on the bottom. Hold on, I got it reversed. Oh, and let me show you how this thing's gonna fail. So as written, I is going from right to left. Therefore, the B field goes in on the top and out on the bottom. Now, let's talk about this, that the magnetic force is ILB, and this I is for 2, the B field is from wire 1. The B field itself is mu naught I over 2 pi R. So as written, this is why I prefer whiteboards, because then I can easily erase that. Question, is the B field at A because of wire 1 greater than or less than the B field at at point B from wire 1. As you get closer to the wire, the B field does what? It increases. So the B field at A must be greater than the B field at B. It has to be. Now the way this thing is set up, what I'm going to do is I'm going to point out why this is wrong. If the B field at A is greater than the B field at B, then the magnetic force at A must be greater than the magnetic force at B. It just has to be. Now, the way that this thing is written, the magnetic force on this wire goes right up, so the magnetic force on this wire is down. And I know I'm going to hear groans coming up in about 5 minutes because I'm going to flip the whole thing over and change it. That current is going from right to left. The B field is out. So its magnetic force is up. Now we've already shown that the magnetic force at A, or the magnetic field at A, is greater than the magnetic field at B, which means that that force must be greater than that force. So this thing has a natural, the way that it's set up has a natural tendency to fall down. Because we've got gravity on this thing as well. And because it's 5 grams, there is a force down with mg as a factor. So if this downward force is bigger than this up force, those two forces are bigger than that force. So FBA plus FG is greater than FBB. And it will never float. So the problem will fail automatically. I'm just lazy. I just copy this stuff from semester to semester. Well, particularly in this summer. So what do we have to do to fix this whole thing? What? What'd you say? Okay, that's a third way. We'd either flip the current in this wire, flip the current in that wire, or take that whole thing and move it up to the top. Let's not do that. So what I'm going to do is I'm going to flip the current in I1 instead of going from left to right, or I'm going to have it go from left to right. The current in this wire is still clockwise. Now the B field comes out on the top and in on the bottom. I cross B means that the magnetic force on A is up here, the magnetic force on B is down there, and I still have mg. So now I can get this thing to levitate, because FBA is greater than FBB. So if I can get that and that to equal this, then it will balance. It will be in translational equilibrium. So the sum of the forces in Y is equal to 0. I'm ignoring the sides. There's a realistic, or there's a real reason to, but let's just forget about it. Only think about those two wires. This gives you FBA minus MG minus FBB. FBA is I2L the B field from 1 at A minus mg minus I2L B field at B. It all equals to 0. Now the big question is, I got to figure out what I1 is. I don't even have I1 in here. But I do know that B is equal to mu naught I over 2 pi R. So this becomes I2L mu naught I1 over 2 pi. The distance from there to there is Y1. Then I have minus mg. I have all of that. And then minus I2L. B field at B is mu naught I 1 over 2 pi y1 plus y2. Because the distance from there to there is y1. The distance from there to there is y1 plus y2. And in the alphabet soup mode, for honor students I would do it, is, because I used to do it as a physics undergrad. We'd be given problems and then they would go, well, solve for I1 and give it in terms of all the other variables. Just give us the equation. We know you can plug and chug. That's just plug and chugging. Let's get it in alphabet soup mode. So let's solve for I1. Move mg over. Let's clean this up a bit. Mu naught L I1 I2 over 2 pi y1 minus mu naught L I1 I2 over 2 pi y1 plus y2. The whole goal is to get I1. So now it's starting to look a little bit better. Factor a ton of stuff out of the right side. A mu naught, an L, an I1, and an I2 all over 2 pi. That leaves me with 1 over y1 minus 1 over y1 plus y2. And I get this. Now I can solve for I1. 2 pi mg over mu naught L I2 1 over y1 minus 1 over y1 plus y2. That comes down. Everything here gets flipped. 2 pi up, mu naught L I2 down, and all of this is equal to I1. So now all I got to do is come up with values for all that garbage. 2 pi, m 0.005, g is 10. Mu naught, let's get the numbers to cancel out well. This is how I kind of do things in for class or for tests. L, I'm going to make it 10. So L is 10 meters. Because I want that and that to cancel. I2 is 0.4, that's given. One of the few things I actually gave you for this. If I had a spreadsheet, I'd really be able to do this well. Oh, and mu naught is 4 pi times 10 to the negative 7. I'm gonna have to get a big number. Let's do y1 is equal to 5 meters and y2 is equal to 2 meters. So 10. So this means I have 1 over 5 plus 1 over 5 plus 2. And that gives me who knows. Oh, what did I do wrong? Yeah, it's the plus sign. Should be minus. Now, the math, hopefully, fingers crossed, it's a big number. But let's just say that the wire is made out of beryllium. It can handle this. It can handle the 1.09 times 10 to the 6th amps coursing through it. It can handle it. It's fine. But that's the number. What I would typically do is if I put this on the test, what I would do is I would play with the numbers in order to get like a reasonable current, like 0.2. That's what I did for test 1. I just sat there and played with the numbers until I got it to work out right. So in this particular case, yeah, the numbers are kind of nonsensical for the final answer, but that's no big deal for me. I don't care. It's the technique that I want you to do. Getting to this right there is 9/10 of the battle. You doing that last bit, whatever. That's just for you guys feeling better about yourselves. Oh, that's another problem. Okay. All right. So the plan is we're effectively, as far as I'm concerned, we're effectively done with new material for test 2. We've got gaps, and we're going to start filling them in. On Friday and Monday, we will be doing those tests that I've posted on Blackboard. So we'll do that on Friday and Monday. And then you pretty much know what's on the test. Let's see. Does anybody have any pressing questions about the problem sets or anything that's due today? Or we all know physics. We all know how to physics. That's great. Hey, really what I'm going to do is I'm going to try to kill 6 minutes and then we'll leave 10 minutes early. Don't tell anybody. I have a particle. Particle has a mass of 2 grams. The particle has a charge of negative 20 microcoulombs. And it is traveling in a circle. And the period of this circle is, I think I can get away with just these 3 bits of information. The period of the circle is 5 seconds. Let's play with it. So it's circular motion, it is in a magnetic field, the charge is negative. Is the B field coming in or out of the page? And why? You've got two choices. The B field can go in or out. Which way is it, at that particular point in the circle, which way is the magnetic force? Up as in out of the page, or up as in physically up the page? Or are both answers horribly wrong? They're horribly wrong, yes. It's a circular motion. Where's the radial acceleration pointing? Radial acceleration always points blank. Center of the loop, center of the circle. So it's always pointing inward. So if it's always pointing inward, the magnetic force has to be pointing inward as well. So what's the magnetic force on a moving particle? Well, magnetic force is QVB. So V, actually I'm going to do it the wrong way first. If V is up the page, which is what it is right now, and B field is in, V cross B is pointing to the left. What did I not take into consideration? We may have to use our full time now. So V is up the page. I've got to get a magnetic force on this negative particle that's to the left. What direction does the B field have to go in? Let's walk over here. Hi, Hiroshi. So what's the magnetic force on a particle? What three things do you have to think about? Could you just read that equation on the left side? What's Q? What's V? What's V? Or magnetic field. What's the in vector description? How do I get the direction of the magnetic force? Yeah, there's a current here. It's Q times V cross B. So V is up the page. I'm going to do that. Well, I'm telling you right now, I'm doing this incorrectly. I think the B field has to be into the page because V cross B points to the left, which is what F sub B is. What did I not take into consideration? Exactly. And what is Q? And it is either blank or blank, and it's blank. What are those blanks? Positive or negative. So if V cross B is to the left, it's a negative charge, which means I flip. Now magnetic force is to the right. But I want the magnetic force to be to the left in order for it to work out. So the way that I have to do this is V is up, B is out of the page. So V cross B is that way. It's a negative charge, which means I flop it to get the desired effect. And so really what we're doing, this is an example of 213, and this may be the thing that I'm going to do for, probably I am going to do it for the test. We're so used to doing A cross B and finding the answer. Now I'm going to give you A cross blank and then give you the answer, or blank cross A and then give you the answer again, and then you got to find those blanks. In this particular case, B is up, the B field has to be out, so that the negative of that value points points in the direction that I want, because the negative particle is traveling counterclockwise. So the B field is pointing out. This force is QVB. It's circular motion. Which means it's mv squared over r for the sum of the forces. Which means it's QVB. One of the v's cancels, and I'm left with mv over r is equal to QB. For the, now one of the things that we sit here and we go, but you didn't give us the radius of the circle. Maybe we don't need that. I gave you the period. Well, what's the period? Velocity is distance divided by time. You can also say that velocity is the distance or circumference divided by the time of one circumference of motion, or the period. So the velocity is the circumference 2 pi r divided by the period. So the velocity is 2 pi r divided by the period. That goes in there. So m over r, 2 pi r over period is equal to QB. And then my r's cancel. And so I've given you everything that I need, or everything needs to be done. The only variable that I didn't give you, and so I'll therefore say, what's the B field? The B field is 2 pi m over period times charge, and that's the B field. We got the direction of the B field through logic. We're getting the magnitude of the B field through the equations. So this is 2 pi 0.002 over 5 times 20 times 10 to the negative 6. And we may end up with a huge B field, but meh, whatever. 2 times pi . So I got a B field of 125.7 Tesla. Okay. It's obscenely large, but whatever. But the setup to get to that point is what's the critical part. Okay. Anything else? Yes.
Why did we drop the negative?
We dropped the negative sign because I said that the logic determined the directions of the B field. Once we have all the directions, I don't care about the sign. I'm only caring about the magnitude. All right, that's it. Going once, going twice. Have fun in lab.